Welcome to this video in which we will develop the notation of a discrete time signal. As indicated in the previous video about sampling, the conversion of an analog or continuous time signal xt to the digital domain is carried out by a C to D converter, which runs at a sample rate of fs is 1 over ts samples, in which ts is the intersample distance. In the discrete domain, the signals are represented as sequences of numbers called samples. A sample value of a typical discrete time signal or sequence is denoted as xnts. Square brackets are used to denote the difference with continuous time signals. Furthermore, in most cases the notation ts is skipped and the samples are simply denoted by xn. Although the independent variable n need not necessarily represent time, n may for example correspond to a spatial coordinate or distance, xn is generally referred to as a function of time with the argument n being an integer in the range -infinity to +infinity. It should be noted that xn is defined only for integer values of index n, and is undefined for non-integer values of this index. Usually, a real-valued signal xn is represented in a graph, from which the correspondence with the underlying continuous time signal becomes clear in case the sampling rate fs meets the Nyquist criterion. Although most information-bearing signals of practical interest are complicated functions of time, there are some fundamental discrete time signals that are frequently used in the representation and description of more complicated signals. The first fundamental signal of interest is the discrete time delta pulse, denoted by delta n, which is equal to 1 for n is 0 and 0 for all indices n, as indicated in the equation and represented in the graph. The discrete time delta pulse plays the same role in discrete time signal processing as the continuous time delta pulse delta t plays in continuous time signal processing. However, in contrast to the discrete time delta pulse delta n, the continuous time delta pulse delta t is a mathematical defined signal, which cannot be realized in practice. Its amplitude is infinite, while its width is 0. The second fundamental signal of interest is the unit step, denoted by un, which is equal to 1 for all indices n larger or equal than 0, and 0 for all indices n smaller than 0, as indicated in the equation and represented in the graph. From this definition it follows that the delta pulse, delta n, may also be written as the difference of two unit step functions un minus un minus 1, while the unit step function itself can also be described as an infinite sum of delta pulses. Another fundamental signal is an exponential decaying function a to the power n un, with parameter a real or complex number from which the absolute value is smaller than 1. An example is represented in the graph. Finally, the complex exponential function e to the power j n omega 0 is also a fundamental signal of interest. It represents a discrete time phasor from which the real and imaginary parts behave as cosine and sine, respectively. Discrete time signals may conveniently classified in terms of their duration or extent. For example, a discrete time sequence is said to be finite length sequence if it is equal to 0 for all values of the index n outside a finite interval of indices. An example of such a finite length signal, as depicted in the graph, is un plus 1 minus un minus 1, which is 0 for all indices n except for n is minus 1, n is 0 and n is 1. Signals that are not finite in length, such as the unit step and complex exponential function, are said to be infinite length sequences. Infinite length sequences may further be classified as either being right-sided or left-sided or two-sided. A right-sided sequence is any infinite length sequence that is equal to 0 for all values of index n smaller than some integer n0. The unit step function, delayed over 2 samples, is an example of such an infinite length right-sided sequence. Similarly, an infinite length sequence is said to be left-sided if, for some integer n0, the signal is 0 for all indices n larger than n0. An example of such an infinite length left-sided sequence is u minus n plus 2, which is equal to 0 for all indices n larger than 2. Finally, an infinite length signal that is neither right-sided nor left-sided is referred to a two-sided sequence. A discrete time signal may always be classified as either periodic or aperiodic. A signal xn is said to be periodic if, for some positive integer capital letter n, xn is equal to xn plus capital letter n for all indices n. This is equivalent to saying that the sequence repeats itself every n samples. If a signal is periodic with period n, it is also periodic with 2n or 3n and all other integer multiples of n. The fundamental period, which will be noted by the capital letter n, is the smallest positive integer for which xn is equal to xn plus capital letter n. If this equation is not satisfied for any integer n, the signal xn is said to be an aperiodic signal. Examples of periodic signals are xn is sine n pi over 4, which has period n is 8 samples, and xn is e to the power jn pi over 8, which has a period of n is 16 samples. The signal xn is sine n, and xn is a to the power n un are examples of aperiodic signals, since there is no integer n for which the signal repeats. A discrete time signal will often possess some form of symmetry that may be exploited in solving problems. Two symmetries of interest are as follows. A real valued signal is said to be even if, for all indices n, xn is equal to x minus n, whereas a signal is said to be odd if, for all indices n, xn is equal to minus x minus n. For complex signals, the symmetries of interest are slightly different, namely, a complex signal is conjugate symmetric if for all indices n, xn is equal to x star minus n, and the signal is said to be conjugate anti-symmetric if, for all indices n, xn is minus x star minus n. Any signal xn may be decomposed into a sum of its even part, denoted by xen, and its odd part, denoted by xon. The even part can be constructed as the sum of xn plus x minus n divided by 2, while the odd part can be constructed as the difference of xn minus x minus n divided by 2. Signal manipulations are generally decomposed of a few basic transformations. These transformations may be classified either as those that are transformations of the independent variable n, or those that are transformations of the amplitude xn, or the dependent variable. Sequences are often altered or manipulated by modifying the independent function variable n, where fn is some function of the index n. If, for some value of n, fn is not an integer, yn is not defined. The most common transformations include shifting, delaying or advancing, reversal, and time scaling. Determining the effect of modifying the index n may always be accomplished using a simple tabular approach of listing, for each value of index n, the value of fn, and then setting yn is x as a function of fn. However, for many transformations, this is not necessary, and the sequence may be determined or plotted directly. Examples of delaying, time reversal, and time scaling such as downsampling and upsampling are illustrated in the plots. Up and downsampling will be discussed in a follow-up video. Shifting, reversal, and time scaling operations are order dependent. Therefore, one needs to be careful in evaluating compositions of these operations. For example, first delaying a signal xn over n0 samples results in xn minus n0. Reversing this signal, that is, replace the running index n by minus n, results in the signal x minus n minus n0. Switching the order of these operations, that is, first reverse and then delay, results in another signal, namely x minus n plus n0. The most common types of amplitude transformations are addition, multiplication, and scaling. Performing these operations is straightforward and involves only pointwise operations on the signal. Finally, the delta pulse may be used to decompose an arbitrary signal xn into a possible infinite sum of weighted and shifted delta pulses. Each term in the sum, xk delta n minus k, can be viewed as a signal that has amplitude xk at index n is k and a value of 0 for all other values of index n. This ends this video in which we developed the notation of a discrete time signal. Thank you for your attention.